Great. So thank you very much for the invitation and the conversation so far. I hope we can keep the exciting conversation going. So what Matt and I wanted to do was just give a little bit of some background to hopefully to talk about some of the things that either the flavor transformation or the neutrino transport people might, in case there's any general broad topics that people aren't already aware of. We just wanted to make sure that all of those are on the table, and then we can. I was hoping to talk about things that need to be done in order to solve some of the big questions in the field. So I'll just, this should only take about 5 minutes, hopefully. So since we already heard a lot about the large scale, some of the recent large scale simulations of neutron star mergers, I wanted to just dive right in and talk about the equations describing the neutrino physics in these neutron star mergers. So to talk in as much generality as possible, I'll just, this equation is referred to as the quantum kinetic equation, and it describes the movement, the collisions, and the flavor transformation of neutrinos. So neutrinos, of course, move at the speed of light, and so they that's accounted for by this advection term. Neutrinos also collide with the background matter and with other neutrinos, and neutrinos change their quantum state. And so the fundamental quantity being evolved here is the distribution function, which represents at each, it's a 6-dimensional quantum wave function. And so at each position in space, and for each value of the neutrino momentum at each position, there is a quantum state that represents the neutrino flavor. This is exactly the same as say electrons, where electrons will have a distribution, and each electron can be in principle a quantum state between spin up and spin down. It's the exact same thing for neutrinos, except it's a quantum superposition of different flavor states. So the particular numerical methods that treat neutrino transport have been shown time and time again to have very significant effects, of course, in neutron star mergers, but also in core collapse supernovae. And so I'm showing here just a recent recent set of simulations from David, showing that depending on the numerical method used to treat the transport, you can get differences in things like the overall abundances of the ejected elements. And on the right, I'm showing a calculation that I did recently, which just shows the magnitude of errors induced by various assumptions in what the radiation field looks like. And so, for instance, one of the popular methods, maybe if people want to, we can talk more about the different methods for treating neutrino transport. But this is a comparison between a Monte Carlo method and a two-moment method. And it just shows that there are differences, that the assumptions used to construct the two-moment method are violated at the order of several tenths of percent. So I'll briefly review the pretty broad phenomenology of neutrino flavor transformation that occurs in both supernovae and neutron star mergers. So there's vacuum oscillations, which come from the fact that different types of neutrinos have different masses and their quantum states aren't aligned. And so as these neutrinos propagate through empty space, they change their quantum state. And this is something that is experimentally confirmed with neutrino detectors on Earth. There's also the MSW mechanism, where in addition to neutrinos having different masses, they interact with the matter that they're passing through, and they feel this as a potential. Different flavors feel different potentials, and so this changes how the flavor transformation proceeds. This is also something that is a solution to the solar neutrino problem, and is also experimentally confirmed with terrestrial neutrino experiments. Then there's collective oscillations, which neutrinos don't only interact with the matter they pass through, they also interact with the other neutrinos that they're passing through. And this makes it a very nonlinear problem. And so the so-called collective oscillations come from a conspiracy between the neutrino mass differences and the potential felt by neutrinos passing through other neutrinos. And so everything from here and beyond that requires neutrinos interacting with other neutrinos there's no experimental evidence for it. It just comes from the same quantum field theory that leads to all the other interactions. You just apply it to neutrinos interacting with neutrinos, and this is what you get. Then there's matter-neutrino resonance, which occurs primarily in the polar regions of neutron-star mergers. This is a result of a conspiracy between neutrinos interacting with other neutrinos and neutrinos interacting with the electrons present in the ejecta. There's the halo effect, which comes from neutrinos scattering off of heavy nuclei present primarily outside of the shock of the supernova. And so the small amount of backscattered neutrinos creates a diffuse halo that can change flavor transformation of the neutrinos. Then there's the most popular thing recently is the so-called fast flavor instability, which is a result purely of neutrinos interacting with other neutrinos. And it essentially happens everywhere in both core collapse supernovae and neutron star mergers. There have been a limited number of calculations to date that have simulated some guess at what this fast flavor transformation does. Right now, it really is just a prescriptive guess. And so these are various different methods of guessing what the flavor transformation does to the neutrino flavor distribution, and it can have significant different impacts on the type of ejecta or the composition of the ejecta. So there's a lot of work currently going on related to this fast flavor transformation. You can look at it from a plasma physics perspective and do a stability analysis. So that is, you take some distribution of neutrinos, you apply a perturbation with some wave number, and you can look at the frequencies of those modes. And if there's an imaginary component to that frequency, it's unstable and it grows exponentially. And so it's an instability. You can also look in existing calculations, for instance, in simulations of neutron star mergers and of supernovae, and we know the properties of the distribution that cause it to be unstable. And so you can find in simulations that don't account for flavor transformation, you can find where in those simulations the distributions are unstable to flavor transformation. And then, of course, there's a number of very small scale detailed simulations of this flavor transformation physics actually happening. And so with fast flavor instability, it generally looks like something like this, where you start with an initial distribution, there's an instability that grows exponentially, and then it settles down into some quasi-fluctuating equilibrium state. So just to get a sense of scale of what all this stuff looks like, this is a plot I like to show. This is for a supernova, just because it's easy to do a plot for a spherical system. It's a little bit more difficult to show it for a neutron star merger system, but the physics is all the same. So this is showing just length scale as a function of position in a supernova, and this gray line is location of the shock in this particular snapshot of a supernova. And this dotted line is just the radius, it's just the coordinate radius. So you can look at, for instance, some metric of the mean free path of neutrinos, and it goes from very small mean free paths to very long mean free paths. And in simulating this decoupling, this transition from trapped deep inside the supernova or deep inside the hypermassive neutron star to free streaming is the entire objective of canonical neutrino transport simulations. We can also look at some other things like the length scale of the separation between neutrinos and the length scale of the de Broglie wavelength, which comes from the neutrino energy, and the length scale of the size of the wave packet, which comes from the time scale of the emission mechanism. And these are all very, very small. And so you might say, well, these length scales are impossible to simulate, so we have no hope. But the point is, because they're so small, they allow us to use fluid-like approximations and treat this as classical transport rather than simulating individual quantum wave packets. We can also look at the length scales associated with flavor transformation. So there's this vacuum flavor transformation length scale, which comes from the difference in the neutrino masses and the neutrino energy. There's the matter term, which comes from the interactions of neutrinos with background matter, and the neutrino term, which comes from interactions of neutrinos with background matter, or sorry, with other neutrinos. And so the point is that these length scales are also very small compared to the collision length scale. And so it's not as clear that there's this giant separation of scale. And so we need to be careful about how we make approximations in order to make these simulations possible. Because if you naively say, well, we'll just resolve it, this is like a factor of 10 to the 7 difference in length scale. And so, it's just, we're not going to just brute force it with simulations that cost 10 to the 28 times as much. Okay. And so that's all the introduction that I wanted to make. Maybe Matt, if you wouldn't mind trying to start off the discussion.
Okay, thank you. So I don't know nearly as much, but maybe I can ask questions since I see nobody's hands are raised. Here's one. Let's see. So I'm often interested in just sort of getting a sense for, how bad our errors actually are. This is one thing that's kind of bothersome about the moment closure schemes that a lot of us use, at least sometimes, is that you doing convergence tests on its own won't tell you how close you are to a solution of the full Boltzmann problem. So by the way, these fast flavor instabilities, you said they go on everywhere. So does this mean that that error from not taking into account neutrino oscillations could in principle dwarf all these other transport errors? Our flavors are just going to be wrong?
Yeah, I can provide my impression of that, and I would be interested in hearing anybody else's if they have opinions. The impression that I get is that the error, it depends on what you're looking at, of course, because no matter what, if you look at your data closely enough, you're going to realize that the simulations don't match nature. If we're looking at things like the composition of the ejecta, I think the errors made from flavor transformation look like they're sort of comparable to errors made from like moment transport approximations. So I don't think that it's going to be dwarfed. I think I would say that it's just as much something that we need to consider. But working on effective means of neutrino transport is still very relevant to get reliable answers.
Okay, looks like Julian has his hand up.
Yeah. Hi. Thanks for the introduction to this subject, which is new to certainly me and I think many of us. A couple of basic questions. Suppose first that you took a homogeneous system with a certain neutrino density, distribution of flavors, energy spectrum, etc. Is it possible to define a threshold condition for the instability?
Yes, absolutely.
And what is it?
So fortunately, it's actually been, there's a nice intuitive way of describing it. I don't have the slide. Maybe I can just scribble on my screen. So if it's homogeneous, you can model your distribution of neutrinos, say, looking something like this, where this is just like, as a function of direction, it just says there's more neutrinos moving in this direction than in this direction. And say that's the distribution for neutrinos. And if you do the same thing for antineutrinos, and it looks something like this, then there's this point that there are some directions along which there are equal numbers of neutrinos and antineutrinos. And this is referred to as an electron-lepton number crossing. And so the criterion, it's necessary and sufficient for instability. These crossings are necessary and sufficient condition for instability.
In fact, we've already raised a question I didn't think to ask, which is when you speak about the flavor transformation, I'd imagine that was electron to muon to tau, but here you've spoken about it in terms of nu-e and nu-e bar.
Mm-hmm.
Is it both? Is it just the neutrino antineutrino change?
So it's the neutrino and antineutrino distributions that derive flavor transformation. But in the case of the fast flavor instability, it does not derive transformation between neutrinos and antineutrinos. So the neutrino antineutrino distributions derive transformation between electron, muon, and tau flavor.
And is there any condition on the distribution of flavor in the initial state? Are there stable distributions despite these crossings in the neutrino antineutrino distributions?
So in all this, I'm assuming that there are equal numbers of all of the different heavy lepton neutrinos. And if you're happy making that approximation, then no, if there are crossings, then it is unstable.
Okay. And you briefly showed a figure that had a probability that dropped from 1 to 0.8 as a result of the instability happening, going nonlinear, and then decaying. What was that probability?
Sorry, this is the survival probability. So this is the probability that a neutrino that starts in an electron flavor state is still in an electron flavor state.
Okay. And what does that say about the long-term result of the instability in terms of the other flavor states? If you started out with all electrons, you lost 17 or 18% of them. Do they go mostly mu, mostly tau, mixed?
Yeah, that's a good question. So in the case for most of these, it's a decent approximation to say that there's equal numbers of muon and tauon flavor neutrinos in both supernovae and mergers, just because the temperatures aren't high enough to create a lot of muons. And so you can generally expect that the flavor will go about evenly to both muon and tauon flavors.
Mm-hmm. Okay. But still having the majority of them remain electron type.
It depends entirely on the details of the distribution. So if you have one of those crossings and the amount of like the area or volume between like inside of that crossing, if that's very, very small, there's not a lot of room for flavor transformation. And so your survival probability, even though it's technically unstable, it might be that only 0.1% of the neutrinos change flavor. And so that's something that is currently not known, is in general, if you have a distribution, how much does the flavor end up changing? And so people have taken a couple of approaches. So like this calculation that I showed here, they essentially parameterize that ignorance, where they try a few different approaches, and that leads to differences. But that is definitely an open question, is how much does the flavor actually transform?
And are there examples in which the crossing is so severe that the density of electron type neutrinos is reduced by a factor of, let's say, 5 or 10 or more? At a really severe large change.
No. So in general, the most severe flavor transformation that I have seen in any calculations in literature, in any of my calculations, is that talking just about the fast flavor instability, is that it goes to equipartition. So 1/3 electron, 1/3 muon, 1/3 tauon. And so that's sort of like a maximum amount of flavor transformation. there are other flavor transformation phenomena, all these things that I mentioned here that can lead to different amounts of flavor transformation. But the fast flavor instability is the most ubiquitous and the fastest of all of these things. So I would say that if there's one to understand first, it's this one. And I would guess that the upper limit for the amount of flavor transformation is complete mixing.
Yeah, so the most naive expectation wins.
Yeah.
There's a question from Harry. I would think, guys, jump in. This is a conversation, so go ahead.
Hello, thank you for your nice talk. You just mentioned about the effective flavor transformation for the short duration simulation, right? Could you briefly explain what is this, actually how the scheme works and how realistic it is? Like, does it include any fast flavor instability in their prescription?
Yeah, so there are two papers now that have done this dynamically within a neutron star merger simulation, and they're pretty similar in the way that they do things, but there are technical differences. And so in general, what this looks like is you do your simulation with standard 2-moment flavor transformation, and you guess at where there's an instability, and then you just like in that time step, you just change the amount of the amount of neutrinos in each flavor. And so in the case of one of these papers, they assume complete mixing. That's Lee and Siegel from 2021. And in the case of this paper here, what they use a different method to test for stability, and they apply a few different things. So I forget which one of these is complete mixing. One of these is the same complete mixing. That is not realistic in the sense that the symmetries in the neutrino-neutrino interaction Hamiltonian mean you have to preserve the net number of neutrinos minus antineutrinos. And so that's not something that's satisfied in general with complete mixing. And so they tried a couple of other schemes that preserve that conserved number. And that does have impacts. Now, whether that's realistic, I don't know. I would say that none of these, I would not rely on any of these as to be realistic. I would rely on them to sort of like probe how sensitive results might be to flavor transformation.
Yeah, thank you very much.
If I may follow up on the previous question, is there also some threshold in terms of the neutrino density and temperature? Because you spoke to this as like an interaction with the collective neutrinos.
Mm-hmm. For the fast flavor instability, no. For the other ones, yes. Well, okay. So for the fast flavor instability, no. For the matter neutrino resonance, no. For all of the other ones, yes. So, and that's because the fast flavor instability, this neutrino-neutrino interaction Hamiltonian is only sensitive to the number density of neutrinos, not to the energy distribution. For collective oscillations and for this halo effect, that is not true.
So typically there's no dependence on the temperature, but could there be on the density?
The density, yes.
Yeah. And
so in general, this Hamiltonian driving everything depends linearly on the density of neutrinos. And so if you have the exact same distribution, but 10 times as dense, everything is going to happen 10 times as fast, and on a length scale, 10 times as small.
Oh, okay, so that's key. So it's the growth rate and the fastest growing wavelengths that scale with density.
Yes.
By the way, was this matter density or neutrino density?
Neutrino density.
Okay.
So one of the things that I was hoping to get out of this discussion is, so neutrino transport is already the most expensive part of these neutron star merger simulations, at least if neglecting things like leakage schemes. As soon as you go to moment-based schemes and more advanced schemes, the radiation transport becomes very, very expensive. And doing flavor transformation, of course, only makes it more expensive. And so I hope I convince you that just brute forcing everything is impossible. And we have to apply approximations judiciously. And so one of the things that I think would be interesting to hear, since we have so many people here, is what input physics do we actually need to resolve the questions at hand? So if I take the stance that we need to self-consistently include Boltzmann radiation transport and flavor transformation in order to understand anything about neutron star mergers, where is that statement wrong?
It's a good question.
Maybe,
yeah. Maybe simplified it.
maybe I can be more provocative and say, given that none of our simulations include all of this, have we learned anything from the simulations that already exist? And so what, by way of doing that, what aspects of the simulations, what aspects of your simulations are needed to make concrete the concrete conclusions that you've made?
That's a much better. Hey, maybe somebody who has done simulations with neutrinos can respond here. I know there is a talk tomorrow about Foucault or by Matt. Maybe you can comment.
Well, David's got his hand up. Let's let him go
David?
first.
Oh, I didn't see him. Okay, go ahead.
Okay, can you hear me?
We do, yes.
Okay, yeah, I'm not sure that I can really answer this question. The only thing I wanted to say is, at some point we will need to do a calculation with as well as we can neutrino transport, even just to be sure that our results are not affected by major systematics. So at least one calculation with full Boltzmann and some form of quantification of oscillation uncertainty will have to be done. And whether then we can proceed with parameter studies where we explore the parameter space and use more simplified neutrino transport or not, this will depend on what we find in that calculation.
Okay, good. And so in that, so you mentioned Boltzmann transport, which sort of accounts for like the numerical method. What about the physics that goes into it? Do you think that we will need to couple all of these things together? So have like inelastic scattering and pair annihilation and flavor transformation and Boltzmann transport and a finite temperature equation state and MHD all in the same simulation? Or will it suffice to do those piecewise and check one by one?
Again, I don't know the answer. I think one of our goals should be to answer these questions, actually. We don't know, for example, you mentioned inelastic scattering with electrons. I don't think we have any idea of whether or not that is important in binary neutron star merger simulations. People in the core collapse supernova context have studied that. We haven't. So that's one of the first things we should be doing, understanding what kind of microphysics needs to be implemented and what is our theoretical error budget that comes with different choices. And this has not been done yet. And of course, if we can, we should be able to, we should at some point include everything and have MHD and Monte Carlo and we should try to understand separately first each bit, whether it's important or not, and what is the associated error bar.
David, since you mentioned the core collapse, and I know that you also work in that community a bit, so what exactly has been learned from that community that one can take maybe or pour it to some degree?
What people have learned, I think, in that community is that a lot of small details matter when you do neutrino transport. I hope that this is not true in binary neutron-star mergers as much as it is in core collapse supernovae, where you change one reaction a little bit and things can change dramatically. But we don't know. So it would be interesting. I think we need to do it. We need, as a community, we need to sit down and explore these different physical effects.
Yes.
We shouldn't be downloading the neutrino tables from Evan O'Connor that I'm sure are really good, but we don't understand what is in those tables, and we run and we see something. We should be trying to understand what is the physics that govern these systems.
Yes. Indeed. And when you say that, you know, these small details matter, but then it depends on the physics question, right? So how much of the physics is shared?
Precisely, your point is very important. That in that context, matters means that the stuff that explodes in one case doesn't explode in the other case. It's a qualitatively different scenario.
Yeah.
In neutron-star mergers, there is no obvious reason to imagine that if we include electron scattering, we will have hypermassive neutron stars that have very different lifetimes and collapse at different times. It may be, we don't know, but that would be something good to know. Hopefully, things are not as sensitive as in core collapse supernovae.
Yeah, no. So there's still a significant amount of work going on in understanding, like you said, the particular interaction rates for all these different neutrino processes. And I think it's also true that, so in order to get correct interaction rates, you need to know the distribution of all of the constituents of the matter. So the number of the protons and neutrons and electrons, and also the nuclei and the quantity of each nucleus and alpha particles, and understanding that the nuclear structure of all of those things and the nuclear structure of dense matter all contribute to these interaction rates in particular. And I think maybe neutron star mergers are interesting in that you get matter at higher densities and more neutron rich configurations in supernovae. And so I think this is also a ripe area to explore some of this, the combination of neutrino transport and nuclear physics.
And in a sense, isn't the consequence of any sort of neutrino flavor change a great acceleration in the rate at which neutrinos can leave the system? Because once they're the actual scattering all involves only the electron type.
Scattering occurs for all three species. It's definitely stronger for electron neutrinos. So I think your point still stands that if neutrinos are able to transform into other flavors, they can escape more easily. So yeah, I think it would in general be like increase the rate at which a hypermassive neutron star cools via neutrinos. Whether that's important, I don't know. First of all, I don't think that these distributions are generally when it's very scattering dominated. You don't have, your distributions are very isotropic, and so you don't tend to have flavor instabilities in those regions. And so I wouldn't say, you know, this is just goes back to, you know, you can never really tell what's happening with the neutrinos, but Yeah, I wouldn't expect neutrino flavor change to be significant in regions where neutrinos are strongly trapped. But maybe it matters in that like outer shell where neutrinos are decoupling, and electron neutrinos and antineutrinos are more forward peaked than other neutrinos. Yeah, is that where you think about the hypermassive neutron star in general, or about other parts of the system?
Well, the parts that are of interest are both the hot neutron stars, and also the debris orbiting it, which is, of course, rather lower in density.
Mhm.
And that's why it actually would be good to quantify that growth rate so that we have at least some rough yardstick, meter stick, to estimate where it's going to be important and where it isn't.
Yes. Maybe let me pull up let's see if I can pull a figure from a paper. So in general, maybe I'll just describe it. So in general, people have looked at like snapshots of neutron star mergers, and you can see that there's instability everywhere. You can estimate the growth rate of this instability because it's proportional, modulo a couple, maybe up to a couple orders of magnitude of the neutrino number density scaled by factors of GF and H bar and C. And in general, where the fast flavor instability exists, it's very, very fast. So you expect dynamics on timescales of like nanoseconds. So like this simulation that I show here at neutrino densities relevant to neutron star mergers and the decoupling region of supernovae. This whole simulation is something like a few nanoseconds. And so those growth rates generally are much faster than anything else that's happening in the system, other than like collisions of electrons. So I think to pretty good approximation, you can take this fast flavor instability as effectively instantaneous. And again, that's not necessarily true about the other mechanisms, but for the fast flavor instability, it is quite fast.
Until the density gets to some low value. We have a very, very broad range of densities here.
Yes. Okay, so we can also look at something like this, where there's like this collision rate, and the relevant length scale for the fast flavor instability is this neutrino interaction length scale. And so there's roughly like a factor of 10 to the 7 here. So if you have collisions, I would expect flavor transformation to happen several orders of magnitude faster. So if that sort of helps with just order of magnitude estimation of where this might matter. But I agree completely, and that is something that you can. Well, this is work that we haven't yet published, but we do have a means of looking at like moment based calculations, and based on those, you can get a pretty good estimate of what the growth rate of the instability is just by looking at the moments.
I'm going to abuse my co-organizing role and call on myself. So, okay. I've been trying to come up with something reassuring to say in answer to your question, Sherwood. So tell me if this is wrong. I want to divide a binary neutron star post-merger system into 3 regions. So first of all, there is the neutrino optically thick, like the interior of the hypermassive star, say, where we're in their diffusion regime. It seems like we are we're almost in a very good state there, right? We know what the neutrino distribution function looks like. It's very symmetric. Presumably this thing you were showing with the asymmetric, you know, new E and new E bar thing can't happen there. I mean, presumably even our moment closure schemes should work pretty well then. I mean, in fact, the neutrino schemes are the ones that are struggle a bit more in those regimes.
Exactly. Yes.
But I mean, the one thing that I guess the open worry, I suppose, would be, you know, we brought up, you know, inelastic scattering, and yeah, if our scattering opacity is wrong, then we get you should still get diffusion rates wrong.
Mhm.
Okay, so but at least that's only one problem.
Plus dense matter, but yeah.
Okay, how's dense matter a problem besides not knowing the equation of state, or do you mean not knowing the
That's
equation
what I
of
mean.
state?
Yeah.
Okay, all right, sure, yeah, so we don't know the equation of state, but that's nothing new. All right, I don't count that as a neutrino transport problem, maybe just to make myself feel better. All right, then I'll jump to the opposite regime. There's like in the poles, we're optically thin. So, I mean, transport is not a problem, at least for, say, you know, Monte Carlo methods, where neutrinos are just following geodesics.
Mhm.
However, if there are flavor oscillations, we're missing them.
Mhm.
You know, again, that's one thing we're leaving out. I have no idea how important it is. Then third, there is the intermediate regime, right? So, you know, this is probably where the torus is, right? You know, optical depths of a few.
Mhm.
So, you know, we're not in comfortably in any regime, you know, so you know, the moment closure methods will suffer from both, you know, the assumption of, you know, what the, you know, what the, you know, there's closure condition, and then also most of them are making assumptions about the energy spectrum, right?
Mhm.
Because they're gray schemes and they're probably both unreliable. It's hard to be optimistic about our treatment of that regime. And unfortunately, that's probably going to be a very important one for outflows.
Mhm.
Okay, but that's only one of the three. And on the other hand, I suppose the Monte Carlo methods presumably work well there. Up to, I mean, you know, there's their usual shot noise issue, which at least is controllable by cranking up number of packets. And, you know, depending on how thick the torus is, you might start the various shenanigans about, you know, implicit Monte Carlo replacing absorptions with scatterings, things like that, but should also be controllable. Okay, I've started rambling now, but is this a
Yeah.
reasonable assessment that at least in a couple of regimes, there's only one thing that we're not doing right?
Yeah, I would say that's true, and maybe I'll say that third regime, like the torus and sort of the transition between the torus and the polar region, is, I think, the most interesting area, because that's where the approximate transport really struggles. That's where we know that there's flavor transformations with, you know, just looking at the transport, there's rapidly varying neutrino distributions as well. And then I will also say that, so we have this this quantum kinetic equation here. So this, I said this term was the one that changed flavor. This is essentially the Schrodinger equation. But this collision term also has flavor structure. And so there are regions in neutron star mergers where the flavor transformation and the collisions both occur at the same time. And so they aren't really separable in you know, you can't really treat one and not the other, because they both contribute to flavor transformation. In general, this will drive flavor transformation, and the collision terms will try to bring it back to you know, Fermi-Dirac equilibrium. But yeah, they both do have flavor structure. So yeah, that disk region, I think, is exciting both for flavor transformation and for ordinary transport.
Yes, I agree. Exciting and the most challenging. You're not in any extreme. No approximation works.
Yeah, exactly.
Yeah. Oh, and by the way, could I also come back to something that David was saying? He said, we shouldn't just be relying on Evan O'Connor to, be updating NewLib. and I agree. I mean, it seemed, although I'm not sure that it means that all of us should be becoming nuclear physicists, but it seems like there's some sort of misallocation of labor, or there's a choke point here where do we need to have more people working on neutrino matter interactions? It does seem a little crazy that this is such a key point of all of our calculations, and there's only one name I can associate with it.
Maybe it's AFK. I will say that, I mean, there's also, there are other neutrino interaction rate libraries. Some of them are open source, some of them are not. So I know, for instance, like an alternative is weaklib, which comes from the Oak Ridge group. And I don't know if there have been any detailed comparisons between them, but.
Can you hear me now?
Oh, yes,
Oh,
yes.
yeah, sorry. You were
So
talking.
my microphone got stopped working for some reason. What I wanted to say is also that we should do an effort to understand what happens in these tables. And, when you download the NewLib table, it contains all the reactions packed together. But we should try to separate them and look one by one at each reaction to understand what is important and what is really the physics driving the system. And also we need to maybe to do the effort to reconsider what approximations have been made in preparing those tables, because it's not obvious that the same approximations that hold in core collapse supernovae will hold for us in neutron star mergers. And I haven't seen anyone looking into this.
Yeah, okay, yes. I think the second reading point was the way I was reading your question. Yeah, and I agree. At least for some value, if we needs to do this.
Yes.
Does anybody have any impression of which processes are maybe poorly approximated? Because there's like a neutrino absorption on free nuclei. And I would guess that that's not, that is probably done fine in NewLib. And neutrino scattering rates on electrons or neutrons or whatever, I would assume that those rates are probably fine. At least my impression is that there's various nonlinear processes like inelastic scattering and neutrino pair production and Bremsstrahlung that are treated quite approximately in NewLib. Although I know Evan and his graduate students are working on removing those approximations, but that still requires neutrino transport schemes that are capable of using those nonlinear interaction rates.
Yeah, one effect I worry about is that in neutron star mergers, the neutrino spheres, where the average energy neutrino thermally decouples from matter, are at much higher densities than in core collapse supernovae. So we may need to worry about correlations between different nucleons. We cannot treat them as free gas of nucleons anymore at 10 to the 13 grams per cubic centimeter.
Vasilios?
Yes, so I'm working at ORNL and I'm actually working on weaklib and currently working on incorporating more modern rates and more modern modern weak physics into those tables, and they're going to be available at some point, and they're grouped by basically how much neutrino energies you have going into the interaction and thermodynamic quantities. And yes, so the original weak-lib set was basically the rates from Brune 85, which is one of those landmark papers in supernova calculations. And yeah, once those newer tables will be up, then I guess they're going to be public, and you can see. So what I'm currently working on is updating electron capture nuclei using actual electron capture tables rather than approximate prescription, because in supernova calculations, that is one of the really important things to get right. But then there's questions of what you actually, once you have that table, what you actually need. So you have like a spectrum, and then you want the integrated spectrum, you want to be equal to the rate of electron capture at a given thermodynamic point. But it's not immediately clear what actual evolution codes are going to need. So if you have a discontinuous Galerkin code, as we're having with Tornado, which is one of the evolution codes that we're working at the lab as well, it's not immediately clear that that's the same, that you actually need the integrated spectrum, or whether you need just point-wise values for the opacities. So yeah, but to that point, there are people working on these tables and trying to make them accessible to the community. So stay tuned, I guess.
Yeah, that's perhaps another good question is what is the need for new numerical algorithms? Because I think so the standard way of doing things is like you said, to have like discrete energy groups, and you can calculate the interactions, and the if you're doing something like inelastic scattering, you can calculate the flux between those groups. But if you depending on the energy resolution that's required, and also the scattering rates, that maybe doing this explicit coupling between different energy groups won't actually work, and we have to do some kind of like energy diffusion approximation, or maybe some discontinuous Galerkin method that takes into account phase space as well. I don't know. Do you have any impression of how much those sort of numerical advances might be required to get reliable merger simulations?
I'm not sure about that. I wasn't really a neutrino expert before I came here to the lab and started my postdoc. So I'm from the numerical relativity side. I guess my impression now, having kind of worked in both fields, is that I feel like in both fields there's the sense that what the other people are doing is really, really complicated, and I feel like in the supernova community, GR seems to be the thing that is really tough, and whereas in the merger community, the neutrinos are really tough, and I firmly agree with that. I feel like the neutrinos are much tougher to do than the BSSN, say, for a merger. But yeah, we'll have to see. The inelastic scattering is another one that's going to be tough to get right? Because there's this delta in the energy that you somehow have to capture, and we'll have to see if you're going to be able to actually pack that in a table or not, or if that's something that you're always going to have to calculate on the fly. So and I'm not sure about yet. That's something that I have to worry about at some point.
Yeah, because right now, does weaklib calculate everything on the fly? It's not like you don't use a tabulated.
No, so weaklib is actually, so you have a base EOS table, SFHO LS 2020, and you have a grid resolution there in rho T and YE. And then the weaklib tables are built at that same resolution, and you can specify the energy resolution for the neutrinos, basically. And so you have the opacity tables are compatible with the underlying US table you build the opacities upon. and then you don't have to do anything on the fly anymore.
Okay. Yeah, so I think that's exactly how newlib works as well. And so making sure that they're consistent is not incomprehensible.
Sorry, maybe hearing the silence, maybe another question. Speaking about numerical methods, are the fast flavor and everything that goes really fast, are those prime candidates to do some sort of subgrid modeling?
Yes, and that is definitely a thrust of the field right now is trying to come up with a reliable subgrid model. So I would say that there have been a couple of suggestions, none of which are like firm, like this is correct, but you know, this is something that's heuristically looks like it works reasonably well. I know several people, several different groups are working along these lines of trying to come up with subgrid models. And so I would say, you know, within a year or two, you'll have your pick of different recipes to use.
Okay. We have, I would say, 4 more minutes before we all conclude the workshop for the day today. Is any more comments to this very interesting discussion?
One further question about the ubiquity of the fast flavor instability. Is there any reasonable regime in which the angular distributions of the neutrinos are sufficiently the same, isotropic, that one of the other flavor changing mechanisms would be more important than the instability?
Potentially, although so that's a good question. One of the difficulties is this these length scales are sort of associated with the different interactions. So for instance, in the case of this matter neutrino resonance, where you have it's a conspiracy between the background matter and the neutrino interactions. Yes, that I can easily imagine that this can be just as relevant as the fast flavor instability in those regions. When you're looking at something like collective oscillations or MSW oscillations, where you have this contribution from the vacuum term, those in general will be much slower, and so I think you would really only have one or the other. However, one complication is that the fast stuff happening inside can pollute the neutrinos that are going out. And so whatever you see in this other region depends on what the fast flavor and other faster mechanisms are doing deeper inside. If you look at something like the inside of the protoneutron star in a core collapse supernova, where there's lots of turbulence going on, there are regions where the chemical potentials of electrons and neutrons and protons are such that the electron neutrino chemical potential is effectively 0. And so the equilibrium distribution for neutrinos and antineutrinos is the same. And so you have isotropic distributions of approximately the same size for both. And there, the growth rates for the instability are still very fast compared to the turbulent time scale of the protoneutron star turbulence. But then it's also not clear what the instability would do, because if there's already in that case, then the chemical potentials for electron neutrinos and muon neutrinos and tauon neutrinos and all the antineutrinos, they're all 0. And so in equilibrium, there's just as many, like there's an even number of all neutrino flavors. And so at that point, if you mix flavors, what does it actually do? That's another open question. my guess is that if you have equal numbers of all the different flavors, it wouldn't really matter anyway, just because you're mixing something that's already mixed. Does that get along the lines of what you were asking?
Oh, yeah, that sounds quite reasonable. And as you can tell by most of my questions, what I've been trying to do is to block out this picture of where in the system these effects are so fast that they just go straight to complete mixing, where there's more competition and that might not, they're important, but that might not be the result, and where the flavors actually are stable and unaffected.
Mm-hmm. Yeah, so maybe I can take a guess at it. I have to say that this is a complete guess. It's just based on hunches, because I think that still has to be established more carefully. But I think one of the things like what Matt pointed out was that inside of the compact object, those distributions are nice and stable. In the near the disk, it's very fast flavor dominated. And so there I would not expect contributions from other phenomena. The polar region, I think, is where you would expect multiple things to start mattering. I hope that's correct. Okay.
Okay.
Well,
Well, thank you very much to the organizer of this discussion session. I think it's a good time now for those of us who need to go to lunch